I mean, all the SATs I was getting.
We'll pull it up during the break and see what we see. Number 4, double check that it's 14 and take a look at it. All right, well, the last section in chapter 10, 10.7. So 10.7 is all about picking the right test. We kind of generically refer to all of them as tests, even though we don't call the geometric series test. But, so when we say there's 10 tests, we mean there's 10 ways to decide convergence or divergence. Some of them are officially tests. Some of them are just, types of series, geometric series, telescoping, p-series, and alternating. Those are the ones I would call the special series. Because if you identify your series as one of these 4 types, then there's a very specific approach that you use. If it's alternating, you use the alternating series test. If it's a p-series, you're not really using a test. You're just identifying what p is, and if p is bigger than 1, you have convergence. Telescoping, again, it's not really a test, but if you have a telescoping series, you find S sub n and take the limit. So this is the hard part, to just sort of look at a series and decide what to do. And that's what we'll try to do today. On the test, I will tell you which of these to use so that you're not spinning your wheels. But it's a good exercise to try to orient all of these ideas in your head to look at a series and try to figure out which one's the best to approach. So this is the list of them all. If you don't have a special test, then we've got our alternates down here. This one is hard. The integral test is hard because it's not always obvious if you can integrate the whatever's, the a sub k. It's not obvious necessarily. But if you get down to here and there's no factorials, the ratio doesn't seem right, if it doesn't have a big power on the outside, so root doesn't seem right, that's definitely something you should ask yourself, is it integrable? And then the 2 comparison tests down here, all we've ever done in this class is compared to geometric series or a p-series. So if you have something that sort of resembles a geometric series or a p-series, but there's like an extra addition or some extra insignificant component to a sub k, that's when you're going to use the comparison test. So the comparison test is usually pretty obvious when you want to use it because it's like, oh, it's almost a p-series or it's almost a geometric series. So then we would go down and use a comparison test. So let's try. Let's take a look at just some randos and see what we would do. So we've got that series there. And we have to decide what to do. Does anyone know what type of series that is? That is going to be geometric. The k is in the exponent position. Now, it's not written in the standard geometric form. That standard geometric form is usually AR to the k, that arc format. The important feature of the standard geometric form is that the exponent is just k, not negative 2k or some constant times k. So the big observation we're trying to make here, once we recognize that it's a GS, a geometric series, we want to force that exponent to be just k. And we know from laws of exponents that if we have those 2 exponents multiplied together there, we can push the negative 2 down onto the 7 and do 7 to the negative 2 and then that raised to the k. So 7 to the negative 2 is 1 over 49, and that will be then raised to the k power. So this is how we could rewrite that geometric series into the standard form. Or at least standard form-ish. Really, geometric series standard form starts at 0. K is 0. But k is starting at 1 here. But it's in that, it's standard form enough for us to go and identify the important features. What is the most important characteristic that we want to identify?
The R.
R, because R is going to tell us whether we have convergence or divergence. So there's R, and then we have to compare that to 1, and it's less than 1. And so for a geometric series, for a GS, is less than 1 converging or diverging? Converging. So for geometric series, ratio test and root test, those three are identical. Less than 1 converges. Geometric series, ratio test, root test, less than 1 converges. Polar opposite of P series, where greater than 1 converges. So we want to keep those distinct. So this tells us that we have convergence. Now, a geometric series is one of the series that we can actually calculate the sum. There's only 2 series that we can calculate the sum for: geometric, telescoping. Those are the 2 that we can find the sum of. So we also will need A. If we're going to find the sum of this series, we need both A and R. And what is A going to be?
149.
A will be 149th because A represents the very first term in the series. We find the very first term in the series by plugging in the very first index value. And so we will, in fact, have 1 over 49 for both. And the sum of a geometric series, infinite geometric series, is going to be what? I think I heard it, A over 1 minus R? That's it.
Something like that.
Something like that, A over 1 minus R. So that's going to be our sum for an infinite geometric series, A over 1 minus R. And we've identified both A and R to be the same, so we'll plug in that 1 over 49 in both places. And my strategy is to multiply everything through by 49. If we multiply all of those pieces by 49, we will end up with 1 over 48 as the sum of this infinite geometric series. So we know it converges. Then we go to the formula that tells us what the value of the series is. Remember that you could, A and R would also be identifiable for a divergent series. So you can always find this fractional value here. It's only meaningful, though, if the series converges. If we have a divergent geometric series, we could still calculate S, but it's not the sum of the series because the series diverges. But any geometric series, diverging or converging, will have an R and an S. Excuse me, an R and an A. So you could plug those into this formula for S, but this formula only makes sense. It only has value for us if we're dealing with a convergent series.
A is just the first term.
A is always the first term. So if this index started at 3, A would be 149th cubed. All right, so whatever that first index is, that gives us the A value. Second series here, it's not a special series. We have the 4 specials. It's not a P, it's not a G, a geometric series. It's not a telescoping series, and it's not an alternating series. So it's not one of those 4 special ones. But we do see something in here that triggers a specific test, which is?
Root test, factorial.
So we have the power on the outside. So the root test is very good if we have a power on the outside, but not so good if we have a factorial. So you're close to the root, the other one that we did on the same day? Ratio. So if we have the factorial, ratio test is always the way to go. Because we've seen that you can't do a lot with factorials. You can't take derivatives and things like that. And so the nice thing about the ratio test is that if you form the ratio of consecutive terms, that factorial disappears. We can get it to cancel. So we're going to use the ratio test. So up here, let me just write that this is a geometric series. So GS for geometric series. This we are going to use ratio test because it has a factorial. So with the ratio test, we're taking the limit of the ratio of consecutive terms. And we are putting absolute values in there. In this case, it doesn't matter because everything is positive. But the generic process would be take the limit of the ratio of consecutive terms. And we always put the smaller term over the bigger term. We're assuming that this is at least, the terms, if we think about a convergent series, the terms are getting smaller. So in that context, we're putting the smaller term over the bigger term. If we're being more generic, we're putting the subsequent term over the prior term. Because maybe the terms aren't going to 0. But generally, when we're thinking about a convergent series, we're thinking about this as a fraction, a proper fraction. But if it's not a proper fraction, it'll diverge. So let's go ahead and use a ratio test here. So we're going to find a sub k plus 1. So we have to replace each of the k's that we see in here with k plus 1. So when we go to the numerator, what will that be over here? When we plug in a k plus 1 here, what will we end up with?
4k plus 4.
4k plus 4 factorial. And when that k gets replaced with a k plus 1, we have 4 multiplied by the quantity k plus 1. That 4 distributes, giving us a 4k plus 4. In the denominator, we will have a k plus 1 factorial, but then all of that is raised to the 4th power. So there's our a sub k plus 1. Dividing by a sub k means multiplying by the reciprocal of what we have there. So we'll have our k factorial raised to the 4th power, and then down below we'll have the quantity 4k factorial. Any part of those two fractions that you want to ask about? That makes sense to everyone? We're kind of looking at these two for some cancellation and these two for some cancellation. So we're going to kind of pair them off and see what we can cancel. So let's focus on this factorial in the numerator. That factorial, we know that a factorial is repeated multiplication by factors that differ by 1. We do repeated subtraction of 1. So 4k plus 4, the next factor would be 4k plus 3. The next factor would be 4k plus 2. Holy smokes, the next factor would be 4k plus 1. And then we get to 4k quantity, and we can put the factorial on that factor. Is that part all right? So if we think about numbers, if we have 9 factorial, we could write that as 9 times 8 times 7 times 6 factorial. We can put the factorial wherever we want, wherever it's convenient for cancellation purposes. So we have that. And then under it, I'm going to put the green stuff here. So then under this one, we have 4k factorial. And we're going to group the other stuff together. So the pink stuff, in the numerator, we just have k factorial quantity to the 4th. Down below, we can do our k plus 1 factorial as k plus 1 multiplied by k factorial. That part? All right, so k plus 1, say again?
Will both of them be to the 4th?
Yes, and so then we're going to have to distribute that 4th power. So the k plus 1 factorial can be broken apart into k plus 1. You subtract 1 from k plus 1 and you get k, and you can put the factorial there. So now all of that is raised to the 4th power, and we distribute that power to each of those. We'll do it in 2 steps just to make sure everyone's seeing it. So then we have limit. Over here, the 4k quantity factorial will cancel. So we are going to have in the numerator all of that other stuff. Let me just grab it. It'll be easier to grab it. So copy, click, paste. Put it there. So this is what is left in our numerator from that part. And then we have still this k factorial raised to the fourth power. And down in the denominator here, now we're going to distribute that exponent. So we'll have k plus 1 to the fourth multiplied by k factorial quantity to the fourth. And we'll see a cancellation here as well. This whole quantity is going to cancel with that whole quantity. So, now we're in a position where the numerator,
How did you get k plus 1 k factorial on the right fraction?
so this right here, that,
Yeah.
so that is coming from here, and it's because k plus 1 factorial, did I write it somewhere else? Maybe I thought I wrote it k plus 1 factorial, remember, is k plus 1, and then we subtract 1, and if you subtract 1 from k plus 1, you get k, and then you could drop the factorial in right there.
Shouldn't that be under the left fraction?
Well, I just moved the green under the green and the pink under the pink.
Oh, okay.
Right, so commutative law of multiplication, we can just move them wherever it's most convenient.
That's what you're doing. Okay.
Yeah, I just want to sort of stack those together so we see the cancellation of these two and then stack those together.
Okay, for sure.
Make
Thank
sense?
you. Yeah.
And then at this point, we are saying, okay, well, the numerator, if you were to multiply this all out, it's just a polynomial. Right? Denominator, if you multiply it all out, it's a polynomial. And we're taking a limit at infinity. And if you take a limit at infinity, it's the dominant term of a polynomial that dictates what the limit value is. So really, all we need to do at this stage is we can just think about what the leading term of this polynomial would be. And that would be the dominant term of each of these individual factors multiplied together. So 4k times itself 4 times. That would be the leading term, the dominant term. So 4 times 4 is 16. 16 times 16 is 256. So we would end up with 256k to the fourth. Now this is only working when we have a limit at infinity that you can get away with doing this. And so since that limit is at infinity, we can look at the dominant term in the top, dominant term in the bottom. And what would the dominant term in the bottom be?
Just k to the fourth.
Just k to the fourth, right? K plus 1 multiplied by itself 4 times. The k times the k times the k times the k is going to give us that leading term or that dominant term. And of course, those k to the fourth both cancel, and we have a limit of 256. So now, this is the hardest part with all these tests. We have to remember what the conclusion is. So what the conclusion is. So this is ratio test. Ratio, root, and geometric series are all the same. They all say less than 1 converges. Otherwise, diverge. So this is bigger than 1, so this is going to diverge. This is greater than 1. So that tells us that we have a divergent series. So that conclusion is always the tricky piece. And if we look at it, what this tells us is that this factorial on the outside is going to be, that's going to sort of win the race to infinity. That's going to go to infinity faster than this is going to go to infinity. In order for a series to converge, the denominator has to go to infinity faster so that the terms will go to 0. If the numerator goes to infinity faster, that's going to drag the values away from 0 so the series can't converge. So the divergence test idea, if the terms don't go to 0, series diverges. Now it's not as obvious to use the divergence test here. We don't have the cancellations that we would need in order to just go straight to the divergence test. So let's take a look at a couple more. All right, so let's look at that first one. Any idea what type of series that is?
Is it a P? Is it a telescope?
So there's not a minus in the main part of the summand. There's a minus in that exponent, but not in the main part. For telescoping, it's got to be two things that are subtracted from each other. So it's not telescoping. Where is the k in this? Is it in the exponent or in the base? Exponent. And anytime we have the k in the exponent where the base is a constant, that's geometric. All right, so this is sort of a modified geometric. We have to fiddle with it to make it a geometric. But if the k is in the exponent and the base is a constant, that's geometric. Like we have all those other weird functions that have a k in both positions. And we have a k in just one of the positions, k in the exponent, constant in the base, that's geometric. And if it's vice versa, if we have k in the base and a constant in the exponent, then it's a p-series. So geometric series and p-series have that difference. One has the k in the base and one has the k in the exponent. But if you have a variable in both positions, not that one, but you have like a 1 plus 1 over k to the k, if you have a k in both, that's when we use like a ratio or a root or something else, because it's kind of like a power tower when you have a function to a function. Bless you. Function to function. So this is going to be, we can manipulate this and put it into a geometric form. So the thing that you're looking at and you're seeing, oh gosh, that exponent is not just k, but we can use a law of exponents here and we can peel it apart and we can make this our first step where we use the laws of exponents to pull apart the exponent that has two terms, and we can create this situation. And aren't these two factors both constants? Those will both be constants, and we can do the following then. So we could rewrite this as the summation. Let's put the constants in front. 3 to the 4th is 9 times 9, which is 81. 5 to the negative 2, that's 1 over 25, but then we're going to flip it. So we're going to get 81 multiplied by 25. So that's the constant part. And then here we can mush those together, and we get a 3/5 if we combine them. And then this will still start at 0. So we have that. And whatever 81 times 25 is, like 2025? Somebody type that in.
Actually, yeah.
2025?
Yeah.
Okay, good. 2025. So, yeah, when I thought of this, I was thinking of it as 8 quarters. If you have quarters, change. 8 quarters is $2.
Oh, sure.
200. Yeah. So 80 times 25, and then 1 times 25, and then add them together without making a mistake. Okay, so now we are in the actual arc/geometric series form where we can identify both A and R here. What is A going to be, and what is R going to be?
Say 2025.
A is going to be 2025. If we plug in our initial index value of 0, 3/5 of the 0 is 1, so we're left with 2025. That doesn't tell us anything about convergence. R, though, will. R is? 3/5. And that's less than 1. So less than 1, which tells us converge or diverge? Converge. Less than 1. Geometric series, ratio test, root test. Less than 1. And because it does converge, we can find the sum of the series. The sum of the series is A divided by 1 minus R. So A is 2025 divided by 1 minus R. Whatever that simplifies to. 5/5 minus 3/5, that's probably the easiest way to do this one. That's going to be 2/5 in the denominator. So it's going to be 5/2 multiplied by 2025. That's not divisible by 2, so we're going to end up with whatever that is. 25, 12. I might need help here.
That's it.
Okay, good. That was close. All right. So that is a geometric series, and it does converge because r is less than 1, and that's what it will converge to, 10,125 divided by 2. So it's very common type of problem where you have to do a little bit of manipulation to get it into a nice format. Focusing on the exponent, you want that to just be k. And so if you see a bunch of other stuff happening with that, use your exponent rules to sort of isolate the factors that have just a k as the exponent. All right, let's look at this thing. What would be the first test that jumps out at you? So this is a constant raised to the k power, so we could absolutely treat this as geometric, for sure. Is there another test that might work also?
The root test.
Root test would also work because we've got that outside power. So either of those are great. When you look down to this base, if you're thinking about it as geometric, then you have a constant raised to the k. Is the value of that constant bigger than 1 or less than 1? Bigger than 1.
Bigger than
Bigger than 1. So if you're thinking of it as geometric, you would say,
averages.
did you say diverges?
Yeah.
Yeah, so it's going to diverge because that common ratio is bigger than 1. So multiple ways you could attack this one. So if you treat it like a geometric series, then your approach is going to be r is equal to e plus 1 divided by pi. E is about 2.7, so the numerator is about 3.7 divided by something smaller than it, 3.1-ish. So this is going to be greater than 1, which tells us diverge. So we would never even consider, that s equals a over 1 minus r. Don't even go there. What would a be in this case?
1.
So a would be found by plugging in k equals 1. And so what would you get?
E plus 1.
Yeah, the same thing, right? So the a is going to be identical to the r. And you could technically calculate s, but it's not going to be meaningful. If we use the root test, let's look at that and see how that goes. So the root test says, let's take the limit of the kth root of a sub k, the absolute value of a sub k, but there is no negative here, so we don't have to worry about it. And this is going to have a conclusion that's very similar. So the limit of this as k goes to infinity. The k's cancel here, so we end up with the limit of e plus 1 over pi. And what's the limit of that?
E plus 1 over
E plus 1 over pi. The limit of a constant is itself. So we're in the exact same boat where we're comparing to 1 now. Again, that's bigger than 1. Geometric series, root test, ratio test, same conclusion. Bigger than 1 diverge. So whether you go with the geometric series approach or you go with the root test approach, same thing. Just kind of illustrates that, yeah, they should have the same conclusion. We end up with the exact same place.
Would this have been a telescoping series if we had k inside the parentheses?
If we had k inside these parentheses?
Yeah. Would that make it telescoping?
It's only going to be telescoping if we can somehow write it like a thing like this. If that was a minus,
Okay.
there's a chance. But we have to be able to write it as a front part minus a back part. And I don't see an easy way that we could do that here. But laws of exponents and things, there might be a way if that k was down inside here.
Okay.
Yeah. Yeah, telescoping, if you don't see it as a difference in two terms, we've only had two other ways to force it to be a difference. One was if we had a log, and we could do, log of the numerator minus log of the denominator and create a subtraction. Or we had that PFD situation where we had a factored denominator and we could turn it into an a over k plus 1 minus b over k plus 2 or something. So if it doesn't immediately have a minus in it, the only two ways we've seen is if there was a log or a PFD, so a factored denominator. Factored denominators. Okay. So we have that thing. Is it, wait, tell me what you're thinking when you look at that. Is it close to something? Is it exactly something? What is your thought? Yes. Compare it to a P series, that's right. Right, is that obvious? No. It's probably not obvious. I mean, if it is obvious, yes, that's great.
The top's like almost a constant.
Yeah, the top is almost a constant. That is the key. Sinc, sine of k, is just wobbling around between -1 and 1, so
Didn't have the 5
it's
plus.
it's almost a constant, because what we've seen is that bounded functions, they behave a lot like constants when you're looking out at infinity. So the numerator is almost a constant. The denominator represents a P series. So that is going to be where we're going. Now, the question, so we are going to use a comparison test, and here is the question. So the B sub k, if we go like this, then P will be 1/2, which is less than 1, which means converge. Now, the question is going to be, in the subsequent step, if we have a series that converges, that's the B sub k series, the A sub k series, in order for it to converge, we have to use our principle that smaller than converging converges. Smaller than converging converges, larger than diverging diverges. So if our P sub k, if our B sub k is a convergent series, we want the A's to be smaller than the B's. Well, you should be able to sort of think in your head here. I'll write it down. Maybe you don't want to write this down right this second, because we're going to change it in a moment. What we would want to show is that the A's are less than the B's. You can write that part down. The A's look like this.
Yeah.
And the B, if we use that specific B, is this inequality going to be true? No, right? Because the denominators match. The numerator here is not smaller than 1.
Doesn't the B sub k diverge? It's a P series that's less than.
Yeah.
Oh, did I say converge?
Yeah.
Oh, okay. Let's switch the inequality symbol. Oh, so maybe it will work then. Oh, good question. Good observation. Yeah. I should have written it down. I should have wrote it down. P less than 1, so that diverges. We've done 3 geometric series where less than 1 converges, so I was in that mindset of geometric series. So 100%, everyone agree? P is smaller than, this is the one that's different than geometric root and ratio. It's bigger than 1 converges, less than 1 diverges. Okay, so this is what are we going to be able, is that true? Yeah, that is going to be true, right? That is going to be true. So bigger than diverging will diverge. And we can cancel out those denominators if we multiply both sides. We end up with that. And we can then subtract 5 from both sides and get down to something we can solve by inspection. Is sine greater than -4? Always, right? The least sine ever is -1. So this is always true. Yeah, so that's true. So that checks out. Okay, so this means our conclusion then is that both series diverge. So both diverge. Both will diverge. So in that one, we could make the inequality do exactly what we want. If this was a convergent series, though, the point I was thinking I was going to make was that if we wanted to show this was less than, we wouldn't be able to show it was less than, right? But what we could do, if we multiplied this numerator here by a constant, would that affect divergence or convergence?
No.
No, if you multiply by a constant, it wouldn't affect it. So if the inequality is not doing what you want it to do, instead of comparing it to 1, you could make that 10. You can compare it to anything you want. And so if you multiplied it by 10, then the inequality would fall in the less than category if that's what we were trying to do. So let's check this one out. This one is probably going to be what I was thinking if I didn't I misinterpreted that P. Okay, so here, same thing. Numerator is like a constant. The denominator is like P series, or is P series if we just look at the denominator. So here, let's go ahead and choose our B sub k to be 1 over k cubed. This one, P is 3, which is bigger than 1, which means converge. Everyone agree with that? Bigger than 1 converge for P. So would we want to show the A's less than the B's, or the A's bigger than the B's? The A is less than the B's. So the B series converges. Our guiding principle then is smaller than converging must also converge. So that's what we would want to show. Now this one, are we going to be able to show that with this inequality? So here is our A. So would we be able to show that? So if this is just a 1, is that going to be true? No. That is not going to be true. But can we fiddle with the B to make it true? What is the most this numerator ever is? 4. That's the largest that numerator ever is. We're using a strict inequality. You could use a less than or equal to if you wanted. But because we are using a strict inequality, 4 is not going to work for us. But we can pick any number we want.
Isn't the highest it could be 7 because you're adding 3?
So it's 3 plus 1. The cosine is always wobbling between -1 and 1. So
Yeah, because the 4 is on the inside.
the 4 is on the inside, so it's not adjusting the amplitude. So the amplitude is still 1. That's adjusting the period. The amplitude of that is still 1. So the most it ever is +1. The least it ever is -1. So 4 would be the maximum value. But we have a strict inequality, so we have to pick a number different than, higher than 4. What number do you want to pick? 5. We could pick 5. Could pick 10. Could pick whatever. Pick whatever your favorite number bigger than 4 is, for sure. So then this still converges, right? Multiplying by 5 is not changing whether that series converges or diverges. It is a convergent series. If you multiply by 5, that would converge to a different number, but that doesn't matter. All we care about is that it converges. So now we're going to be able to show that this is true. So first we'll multiply away the k cubed. Multiply the k cubed away. We'll just isolate the trig function so that we're down to an obvious spot where we can solve by inspection. And this is true. That's a true statement. And so that tells us then, if that's a true statement, that tells us that the A series is smaller than the B series, and the B series converges. This tells us that the A series converges. So therefore, we have converged. So both series converge. Good. Couple more. What test?
The rat or whatever. It has
Root.
something on root.
Yeah, the root test. The radical test. The radical test. So the root test here, we could rewrite this once if we care to. We could write this as k divided by k plus 2 all to the k. So notice that this is one of those funny functions where both the base and the exponent have a variable. So it's like a function raised to a function. So those are the most complicated scenarios to attack. or maybe not most complicated to think about, perhaps. I mean, this one's pretty easy to attack with the with the root test. So we're going to go root test. And we're going to take the limit as k goes to infinity of the kth root of the absolute value of this. Well, nothing's negative there, so we don't really need the absolute value. So we don't even need to put it in. So we get that. So these expressions with a k on the outside as a power are super nice with the root test, because then the power just goes away. And we are left with this limit right there. And what is the value of that limit? 1. So we've got polynomials of equal powers. So we take the quotient of leading coefficients. Or you could divide everything by k. 2 over k would go to 0. You'd have 1 over 1. So we get a 1. So now we're in that scenario again where we have to decide what that means.
Inconclusive.
Say it again?
Inconclusive.
Inconclusive.
Yeah.
It's inconclusive. Like, oh, crap. It's inconclusive. All right, so that means we've got to do something else. So the root test is great when it works. It doesn't always work, but at least we can get to the point where we can tell whether it worked or not really quickly. Root test is pretty fast. Okay, so this is inconclusive. What about the divergence test? What about the divergence test here? Yeah, that's the one that we haven't really talked a lot about. It's one that you should, at least in your mind, be thinking about. Sometimes the limit is so hard to do that you just jump to the root test or the ratio test because it's like taking the limit to decide if it goes to 0 is not obvious. But this does remind us of that E thing, right? A little bit like that. We have our E shortcut. We have our 1 plus A over K to the B times K. We have that goes to E to the AB. It looks a little bit like that. Like if we could flip the inside of this. Let's try. So let's go divergence test. So divergence test just says take the limit of a sub k as k goes to infinity. So we're going to take the limit of a sub k as k goes to infinity. But I'm going to flip this. Because in order to get two terms here, we need to have the fraction be reversed, inverted, so that the one term is in the bottom so that it could distribute into the numerator. So if we flip the base and make the base k plus 2 over k, what has to happen to the exponent?
Minus k.
Minus k, exactly. Right? That exponent sign, if you change it, then you flip what's below it. Okay, now we can then say this is 1 plus 2 divided by k to the negative k. Now we're in our shortcut exponential form. And what is the limit of this?
E to the negative 2.
E to the negative 2. So this is 1 over e squared. And what is the conclusion with the divergence test?
Diverges.
So that diverges because why?
It's not equal to 0.
Not equal to 0, therefore diverge. Right? Exactly. So not 0. The divergence test says the only chance you have of convergence is if those terms are going to 0. That's the first necessary condition, is if the terms don't go to 0, the series diverges. But then we have all these nuanced cases, like the harmonic, 1 plus a half plus a third, that diverges even though the terms are going to 0. They just don't go to 0 fast enough. So here we have one of those egregiously divergent series. The terms aren't even going to 0. If the terms aren't even going to 0, the thing diverges instantly. approaching it with the root test first, though, that's what most people would do. Because you look at that and you're like, oh, okay, we can get rid of the k, and we can get to this place really quickly. But we have to remember, for root and ratio, if we end up with a 1, it's inconclusive. Okay. Okay, this one is also screaming at us to use the root test. Let's rewrite it once. We'll rewrite this as, well, can we rewrite this easily? You tell me. Can we do something with that numerator? Can we combine the 2 to the k and the 3 to the k?
So like 2 times 3 to the k, so is it 6?
So tell me this law of exponents first. Actually, let's put it on the board because laws of exponents sometimes can be. So if you had a times b raised to the k power, how could you distribute? Could you distribute that k in a way? Could you rewrite that as
You could do a to the k, b to the k.
a to the k, b to the k? Good. So you could do that. So that tells us that we could rewrite this as 2 times 3 over k, all raised to the k, right? You agree?
Sure.
Okay. So we could then, if we want, we could combine these numerators here, the 2 term factors in the numerator. We could write this as 6 over k to the k. Write it that way. Okay, so now let's go root test. Also notice again that this is like one of those funny functions where it's f to the g. You've got the k in both positions, the base and the exponent. So root test says take the limit as k goes to infinity of the kth root of this. We're going to take the kth root of all of this. And once again, it just gets rid of that really quickly, that exponent on the outside. So we get 6 over k. And what is that limit as k goes to infinity? 0. So that limit is 0. Now we have to make our conclusion with the root test. This is less than 1. That tells us
It converges.
converges. Yeah. So for geometric ratio root, less than 1 converges. So there, the root test works really nicely in that case. All right. Let's go to our last slide here. Eek. So sine of 1 over k to the 6. What do you think?
Divergence test.
So let's try the divergence test. That's always a good test to consider. A lot of times you can do it in your head, but let's write it out this time just to make sure. So as k goes to infinity, the limit of a sub k. And what is that limit going to be?
Like nothing.
Like nothing.
Yeah.
0, right? Right, as k goes to infinity, we are taking the sign of 0. So the sign is a continuous function. So the limit jumps inside. 1 over k going to infinity, 1 over k to the 6 as k goes to infinity is going to be 0. So this is going to be sine of 0. Sine of 0 is 0. So this means that this is inconclusive, right? Inconclusive for the divergence test. So inconclusive. Inconclusive for that. Any other ideas?
The integral test?
So we could try the integral test. Let's think about it. So if we could integrate, we can integrate sine of x for sure. But can we integrate sine of 1 over x to the 6? If we wanted to integrate sine of 1 over x to the 6, we'd need some sort of substitution thing to work. We'd have to let u equal the inside 1 over x to the 6. The derivative of that, you'd make it x to the negative 6, and the derivative would be negative 6x to the negative 7 or whatever. And there's no extra x's on the outside that would allow substitution to work. So we're not going to be able to integrate it because that's too complicated.
Isn't it really similar to a p-series?
The inside is similar to a p-series, so maybe we can compare it to a p-series. Maybe we should compare it to a p-series. Let's see. Okay, so let's think of, so do you want to compare it to 1 over k to the, let me ask you this first, because there's an idea in trigonometry that you may or may not remember. Let's take a look at a picture of sine of x versus x. So when we are looking at this guy here, this is the angle. All right, that's acting like theta. Right, that's like theta. And when you're on a unit circle, we are in a unit circle where that's theta, and it's a unit circle, so this is 1, 0 over here. This arc has what measure? What is the measure of the arc on a unit circle? I'm going to use a different color to represent the arc. How long is that arc? So we have a formula from trigonometry that says S, the arc length, is equal to R times theta. But if you're on a unit circle, what's true?
R is 1.
So if R is 1, that tells you that S and theta are the same. So the angle and the arc are the same. So this arc right here also has a measure of theta. Those are the same length. Okay. Just that that angle is rotational. It's measured in radians, and that arc length will be measured in whatever, inches or centimeters. But they have the same magnitude. If that's pi over 6, that's pi over 6. It's just that this would be pi over 6 units of length, whereas this is just pi over 6 radians. This is only true if we're in radians. Have to be in radians. So now let's draw a picture of sine of theta. We know that sine of theta is right there, correct? On a unit circle, that purple segment is sine. Cosine is horizontal, sine is vertical. Do you see from this picture that sine of theta is less than theta? Can you see it? Right? That arc is longer than that vertical segment. So we have this property, and in Calc 1 sometimes you prove this using first derivative test or something. You could make a function that represents the difference between the two. You can get a minimum, you can take a derivative, you can do all this stuff, and you can prove that this is true. For us, we don't need to prove it's true. We can see it's, I wrote it right. Sine of theta is smaller than theta. When we get into chapter 11, we are going to see this again. We're going to see the comparison here. So that is the idea that we are using here. So if we choose as our p-series 1 over k to the 6, let's see what happens. So if we choose 1 over k to the 6, p is equal to 6, which is bigger than 1, so converge or diverge? Converge. Bigger than 1 for a p-series converges. So this tells us converge. So then we would want to show that the A's are bigger or smaller than the B's? Smaller. We would want to show this because smaller than converging converges. So here are the A's. So sine of 1 over k to the 6 is that less than 1 over k to the 6? And the answer is yeah. Sine of theta is less than theta. Right? The theta is the inside here. Sine of the inside is less than the inside. That is true. We've just looked at this right here. This is true. So this tells us that both series converge. So both will converge. So we do need to know this basic fact, though, that sine of theta is less than theta.
And that's true all the way through that first quadrant?
Yeah, it's true when we're dealing, it's true. It's true as long as theta is positive. As long as theta is positive. Even in quadrant 2, it's still true. Like it gets even more true in quadrant 2. Like if you're here, your sine of theta is there, your sine of theta is that, and your arc length's even bigger. So it's even more true if that's a correct thing to say. It's like being more pregnant. It's either true or not true. You're either pregnant or not pregnant. You're not more pregnant or more true. But you know what I mean.
And then if it were cosine, it would be...
Cosine is different. Yeah, cosine is different. And with cosine, what we look at is this little piece here is 1 minus cosine. And that little piece right there. So sometimes you'll do a comparison between the arc and 1 minus cosine. Okay, all right. So let's finish this last one off, and then we'll take our break. And we'll start fresh in chapter 11. Okay. So this one kind of has that shortcut e vibe to it, but the exponent is k squared and not just k. So we're not going to be able to use that shortcut e thing with the divergence test that we've seen. We are going to go straight to the root test here. Feels like we've got some funny business going on in here, though. But let's see what happens. So let's see what happens when we go with the root test. So we're going to take the limit as k goes to infinity. And we're doing root test because we see this root out, this power out here. So we're going to take the kth root of all of this. If we wanted to, we could get rid of that minus sign. If that minus sign is kind of, bless you, if that's kind of bugging us, we could definitely do this if we want. Maybe it's a little easier to take the kth root of just k squared. I don't know. Doesn't really matter. We'll see if it was helpful to us or not in a minute. So now we have k plus 8 over k to the k. As k goes to infinity. That now is in our shortcut e form if we do this division. All right, now it is in our shortcut e form. What is that limit?
E to the 8.
E to the 8, exactly. All right. So now we're using the root test. We found our limit. It's not 1, which is good because we see that the limit being 1 means it's inconclusive and you have to dig deeper. We don't want to dig deeper. So we compare this to 1. It's bigger than 1, certainly. So what is the conclusion when we have a value bigger than 1? So remember that root and ratio act like geometric series. Smaller than 1 converges, bigger than 1 diverges. That's going to diverge. Yes. So here is a really quick root test that generated some divergence. Yeah, very nice. Yeah, root test is fast when it works. Whether it's for convergence or divergence, it's pretty fast. As long as that limit's not 1, you're psyched. All right, let's go ahead and take our 10-minute break, and then we'll jump into power series. Power series, an infinite collection of infinite series, when 1 is not enough. 1 series is not enough.
So no telescoping? You didn't want to go through all of that pain?
I didn't want to go through all that pain. Oh, but the pain I do want to go through is that number, did you say it was 14?
No, it was just.
Okay, chapter 11.
Ask for another question.
Delay. Distract. I'm very distractible. Okay. So, this is probably the most important section going forward if you're going into engineering. If you're going into engineering, understanding power series is super important. The idea, when you're an engineer or a scientist of some sort, you're going out and collecting data, or you've hired some minion to go collect data for you. Ideally, that's the case. Although it's fun to collect data for a while, I think, but then you get bored and you want someone else to do it for you. And the idea is that you have all this data, and it creates, you have this rate data. You're measuring rates of change of different variables, and so you've got this pile of data, and you want to match it to a function. Because we can, all this stuff you've done in Calc 1, 2, and in Calc 3 eventually, you're analyzing functions. And so the idea is if you can turn your data into a function, then you can use calculus to analyze it. And the problem is this. So let me give you an analogy first. If you take the set of real numbers, the number line, and you just pick a number off, it's either rational or irrational. What is the likelihood that it's rational? Very, very small. 99% of the time you pick a number off that number line, it's going to be irrational. But what do we do in real life? We use rational numbers for everything. I mean, us in math and science, we're comfortable with square roots of 2 and pi and some of these irrationals. But the average person never deals with irrational numbers. They deal with rationals. But unfortunately, most numbers are irrational. And the same thing happens with functions. If you think about this big cloud of functions and you just pick a function out of it, the chances that it's an elementary function, like sine or cosine or e to the x or whatever, hyperbolic cosine, the chances are close to 0 that when you pick a function out of the function cloud randomly, that it'll be an elementary function. Okay, so it's a generalized function. And a generalized function is a power series. What we are going to see is that all of our common functions can be written as power series. A power series is simply a series of powers of x. That's what a power series is, the series of powers of x. And it turns out that all of our elementary functions can be written as power series. So we'll come back to that slide in 1 second, or that part of the slide in 1 second. So here are 2 examples of power series. Most common function that we see in engineering typically is a sine, a cosine, an e to the x, or a log, one of those. Here's the power series for e to the x. So e to the x can be written, some folks will refer to it as an infinite polynomial. We got to be careful with the word infinite, though. What we mean by infinite in this case is that the powers of x go to infinity. I like to call it a never-ending polynomial. So it's a polynomial that goes on forever. It's never-ending. And it's amazing that you can write this function as a polynomial, as an extended polynomial, a generalized polynomial that goes on forever. It's kind of amazing. And so it turns out that you can have power series that are just like you can have parabolas centered at the origin, right at the origin, or you can shift them. You can do the same thing with power series. This power series is centered at the origin because it's just an x. This power series here, you can see that every term has an x minus 1. It's just like shifting the parabola. So this power series has a center of 1. So the center is always the 0 of that little parenthetical quantity. So up here the center is 0, down here the center is 1. So all of these functions that we deal with can be written as these infinite polynomials, these never-ending polynomials, these generalized polynomials. When you pick one of these functions out of the cloud, a generalized polynomial, the chances that it happens to turn into a common function, close to 0. Close to 0, right? These have very specific coefficients. And you just think about tweaking one coefficient. If you just tweak this one coefficient, then it doesn't have an elementary function name. It's going to be like an irrational number. It's going to be nasty. And so what do? We approximate. So we've talked about the remainder and how you minimize the remainder. You have to go further out in the partial sum. And so that's going to be the idea, is that we, when you get into engineering and you're not getting these common functions, you have to be able to use them in general. You have to be able to use these generalized functions, which are power series, in order to solve differential equations. Because your data is coming back, it's going to generate a differential equation. Differential equation is an equation that relates the rates of two different variables or more variables. And then you're going to generate the solution to a differential equation we have seen in this class as a function. But if your function doesn't have a nice compact name, if it's not an elementary function, then it's a power series. And so then you have to solve your differential equation with power series, which you'll do in ODE 1 in the regular differential equations class. You'll start to solve differential equations with power series. So that's why they're so important, because in general, that's the solution to a differential equation is a power series. So when you look at this box up here, it looks much nastier than it is. And when you look down here, it's a little bit more manageable. You see that it's just powers of x that go on forever. It's a never-ending polynomial. And we've got these coefficients. If those coefficients aren't really nice, there's no chance that you have an elementary function. So again, that one is centered at 0. This one is centered at a. And the c sub k's are just constants. So these are two of the most common ones. We are going to see 12 different power series. On the exam, I'll pick 5 of them, and I'll tell you ahead of time which 5 you need to know, because they can be hard to remember. But I will show you some patterns that will make it easier to remember. So the e to the x one is so important. That one you want on your note cards immediately. No one really is ever going to ask you to memorize the natural log one. It's much more complicated. But that one you see so much, the exponential function. Why do we see the exponential function so much? Because it is the solution to the most basic differential equations. That is why. It is its own derivative. And when you get into differential equations, you start thinking about population changes. The rate at which a population changes depends on the current population. And so it turns out that the solution to that idea is an exponential function. The function that has its own derivative. Okay, so never-ending polynomials. Never-ending drama, never-ending fun. Let's go back to Calc 1. So in Calc 1, so there's going to be another perspective to these infinite polynomials. The question is, well, how do we generate them? If I give you e to the x, how did we come up with that never-ending polynomial that is equal to it? That's equal to it for all x. How do we come up with it? And the idea is rooted in tangent lines. That's where it starts. So it turns out that you can build these never-ending polynomials with repeated derivatives, going from tangent line to concavity, all those things, which we don't have names once we get past concavity, but we have slope and we have concavity. First derivative is slope, second derivative is concavity. So here's what we're going to do. Let's go back to Calc 1. We've got our function, black curve. There's our tangent line at the point a comma f of a. All right, down here at the bottom, I remind you how you find the equation for the tangent line. You take your point slope formula. This point right here is a comma f of a. The slope of this line is the function's derivative evaluated at a. So that's how we get the tangent line. And this is the form you usually use it in Calc 1. Until you start doing some approximations, then you may rewrite it and isolate the y and write it this way. So that is the tangent line right there. F of a plus f prime of a times x minus a. The a is a constant. The only variable is that x. All right, so the best linear approximation is the tangent line. And we are going to start calling our approximations p. So p sub 1 is the best linear approximation, power of 1. P sub 2 will be the best quadratic approximation. We'll call it p sub 2, 2 for quadratic. P sub 3 will be the best cubic approximation. P sub 4 will be the best quartic approximation. P sub 5 will be the best quintic approximation. In Calc 1, all you did was the linear approximation. How boring. We are going to now do the best quadratic, the best cubic, the best quartic, the best quintic. All these approximations get better and better and better as you go further out with the derivatives, with the power. So the two key properties to the tangent line, so the tangent line is the P1. The key properties are these, that the value of your approximation matches the value of your function at A. All right, so that's the first thing. They've got to match in value. The second important property is that they have the same slope. So the tangent line is only a good approximation because its slope, the slope of the tangent, is the same as the slope of the function. So when you're looking at this curve, the slope of the curve is the slope of the tangent line. So the slope of the curve and the slope of the tangent line match. All right? So that tells us that these two things match for your polynomial that's approximating and your function, same value, same slope. Okay? That's how the best linear approximation, that's why it is the best linear approximation, because it matches in value and it matches in slope. Now Now we want to get the best quadratic approximation. So the best quadratic approximation is going to have an extra condition that must be met for it to be useful. We still want the value of the polynomial and the value of the function to match. So we want values to continue to match. We also want slopes to continue to match. Now we also want concavity to match. So the blue is the best quadratic approximation to the black curve at that point. It's going to have the value matching, it's going to have the slope matching, and it's going to have concavity matching. So it's going to have three things that match instead of just two things. So here's how we build the best quadratic approximation. We start with our tangent line, and then we need to add a quadratic term. So we're adding this quadratic term with these three principles in mind down here that we want value, slope, and concavity to match. If we make our quadratic form, our quadratic term, have a form that has an x minus a in it, notice that if you plug in a for x, these two terms disappear. And we need that to happen so that we end up with p sub 2 of a is equal to f of a. Right? This tells us that the values match. The only way the values can match when you plug in a is if this term goes away. Right? The value of the function is right here. F of a is the value of the function. If we want p sub 2 of a to match f of a, then these have to disappear when you plug in a for the x. So that quadratic term here has to have an x minus a so that it disappears and allows us to have this value continuing to match. Similarly, the derivatives have to match. So for the derivatives to match, the derivative of p sub 2 of a, let's check it out right down here. Let's make sure we know how to take derivatives carefully. So here's p sub 2. If we take the derivative, f of a is a constant. Derivative of a constant is 0. So that part is 0. Now let's focus on this right here. The derivative of that, I claim, is that. Do you agree? F prime of a is a constant. That constant gets multiplied by x. That constant gets multiplied by a, which is also a constant. So when you differentiate this here, if you were to write that out, you have f prime of a multiplied by x minus f prime of a multiplied by a. So if you differentiate that, this part's just a constant. Derivative of that's 0. What's the derivative of this?
F prime of a.
F prime of a. It's the coefficient of x. Right? If this was 5x, the derivative would be 5. This is a constant that's sitting in front of x. So this is the derivative of this whole expression, right? Because the derivative of that part is 0. This is just linear. Derivative of a linear expression is the constant. So f prime of a is the derivative of that. And now we take the derivative of this last term. We use the power rule. 2 comes down in front. We subtract 1, multiply by the derivative of the inside, which is just 1. So we end up with that. So let's check. If we plug in a for this first derivative, do we get that p sub 2 prime matches f prime? Let's check. So we plug in a for the x. This goes away. And we have that f prime of a would equal p sub 2 prime of a. If we plug in a for both those x's, this term goes away, and we will have the p sub 2 prime matches f prime. So now we have the value matches, we have the derivative matches, and now the third piece we want, the third condition that we really are enforcing, that's our new condition. So we now have the two old conditions matching. Value and slope are matching. Good. We also want this to match. So take the derivative again. So now we're differentiating this thing, p sub 2 prime. Well, this is a constant, so its derivative is 0. So these two things go away. So now we're just differentiating. The only thing left to differentiate is this part right here. And isn't the derivative of that this random constant times 2, 2c2? Again, same idea. If you distribute that 2c2, 2c2 is a constant, you multiply it by x, you multiply it by a, and then you're going to take the derivative of all of that. Aren't you getting just this? Derivative of this constant is 0. Derivative of this linear expression is 2c2. So this is where we're at. And we're forcing this to be true, so the second derivatives have to match, the concavity has to match. Well, the second derivative is a constant. So if you plug in a, you get 2c2. So that tells us that these things are now matching. We are forcing that to be a condition that we are going to impose on this polynomial. So that extra term that we add will allow us to conclude that. Because if we take the second derivative of p sub 2, we get a constant. And so now we can say that whether you plug in a here, if you plug in a right there, that's going to be the value of p double prime. It's going to be the value of f double prime also. We're forcing that to be true. And if we force that to be true, f double prime of a can be put right here. And if you divide both sides by 2, you can solve for that constant. That constant then gets put into our general expression. Now we have the best quadratic approximation. These guys here are all coefficients or constants. And you can see a pattern forming really clearly. And that pattern is going to become super obvious as we continue. So f of a, f prime of a, f double prime of a divided by 2. Do you see that the 2 is matching the number of primes? Okay, that's going to continue. So now you can say to yourself, oh, what's the best cubic approximation? Go through the same process. Best cubic approximation, we're going to add a c sub 3 x minus a to the third and do the same thing. And we're going to end up here. Oh, no, not yet. We'll do the third approximation after this slide. Okay, so let's use these. So we understand the best linear approximation. Now we've just talked about the best quadratic. Let's use those two before we extend it to the third and fourth approximations. So what do we do with these two approximations? Okay, let's put off in the corner here that p sub 2 of x, so this is going to be the best quadratic approximation. It's going to be f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a squared. So that is our best quadratic approximation right there. And it includes p sub 1. This part right here is p sub 1 of x. So the best quadratic, we have to build the best linear to get to the best quadratic. So I find it easiest to set up a table. We need the first derivative of f and the second derivative. So I usually will start out, and I like to use y just because it's a little less onerous than writing f of x, f prime of x. It's a little easier to start with just a y. So I'm first going to rewrite the function in an easily differentiable way. There's y. So that's f. Y prime, we all know, is minus x to the minus 2. And if you wanted to, you could write this as minus 1 over x squared. This one, of course, you could write as 1 over x, but we're going to leave it in these differentiable form here. Y double prime is going to be positive 2x to the minus 3. If you wanted to, you could write this as 2 over x cubed. So that's how far we have to go out. If we wanted the best cubic approximation, we would need one more derivative. Best quartic approximation, another derivative after that. Now, focusing on these coefficients, notice that we have to plug a into each of those. They tell us that we are going to center this polynomial at 1. Centering the polynomial at 1. So now let's evaluate. We have y of 1. So this is y of a, f of a. Plug in a 1 there, we get 1. And then we need y prime of 1. That's going to be negative 1. Then we need y double prime of 1. That'll be 2. So those are our three coefficients. Now all we have to do is monkey see, monkey do. So p, let's write down p1 of x first. So p1 of x is f of a, that's this one, 1, plus that coefficient, which is negative 1, multiplied by x minus 1 to the 1. So a is 1, so that becomes a 1, x minus 1. And then we have plus, second derivative is 2, but we have this extra division by 2, and then we, oh, wait, this is linear. So there's the best linear right there, we're done. We will not simplify that. You can if you want, but in general, it's going to be way easier to not simplify this thing. You could distribute this and turn this into 2 minus x. That's a bad idea in general because we're going to want to establish these patterns, and sometimes we're going to want to go backwards, and if you simplify, you won't see the patterns. So you could do that. That is technically correct, but we are going to leave it in this form right there. All right, so p sub 2 is going to be p sub 1, but then we have to add second derivative. So 2 over 2 times x minus 1 squared. The simplifying of these coefficients, sometimes we're going to do it, sometimes we won't. It kind of depends on the context. But either one of those, you certainly do not ever square this out and then add them. That'd be a total waste of time. So that is our best quadratic approximation. So now we have to figure out how to use it. So that is our best quadratic. Right there. So we've got our best quadratic, and this is the form of the best linear that we're going to look at. So let's see what happens. Let's move this guy. So when we look at this, we are trying to approximate 1 over 1.05. So 1.05 in the denominator. So that's going to be approximately equal to the tangent line evaluated at x. So what is x in this case?
1.005.
So x is the denominator, right? X is the denominator. So x is the denominator here. So what we're going to plug in then for this x is 1.05. That 1.05 is going to get plugged in for the x's that are in our approximations. Because that's what x is representing. X is representing the denominator. So 1 over x, 1 over 1.05 is approximately equal to whatever these things are with the x replaced with 1.05. All right, so this x gets replaced with 1.05. Therefore, these x's get replaced with 1.05. Fair enough? So this is going to be 1 minus, we can take away the multiplier of 1, 1.05 minus 1. So 1.05 minus 1 is 0.05. 1 minus 0.05 is 0.95. So that tells us that that is our best linear approximation. Now, if we want our best quadratic approximation, it's going to be that 0.95. That's going to be the simplification of this whole first part. All right, we could cut to the chase there, put the 0.95 there, and then it's going to be plus. Here, we're plugging in the 1.05. Minus 1 is 0.05 squared. So 0.05 squared. Everyone okay with that? So we're taking the 1.05, plugging it in for each of these x's and simplifying 1.05 minus 1 is 0.05. Now we have to square it. So we have 0.95 plus what is that going to be, by 0.0025? What was that question? You can ask it. This one right here? That one?
The E2, after the, you said that you can say that 0.95 is E1?
Yes, 0.9, because in here,
Plug it in.
oh, did I do my math wrong?
No,
Let's see.
I thought our x was 1 over 105.
No, the x is only in the denominator.
No, but the approximation is 1 over 105.
Yes, so we're approximating 1 divided by 1.05. The role that x is playing is whatever's in the denominator.
Okay.
So to get from 1 over x to 1 over 1.05, we replace the x with 1.05.
Okay.
So that's why we're going to replace all the x's with 1.05. And then down here, when we do this subtraction, you end up with 0.05 when you do that subtraction. And then 1 minus 0.05 is 0.95. River, are you following?
No, that was, yeah.
So here, so here, this minus 1 right there, we don't need to put the 1 in front because it's multiplication.
I think she was talking about
The
the
second
2
one,
over
it's the
2
same
turned into
reason,
the
so
1.
it doesn't really matter.
Oh, yeah. Oh, yeah, same thing. Same thing. It's multiplication by 1, so we don't have to put it in there.
Minus 2.
And so this right here is 1 multiplied by that, but we don't need to put it in. And did I multiply 0.05 by itself correctly? So this is our best quadratic approximation. So what we can do is, because all these problems in the beginning are going to be very cooked up, we can actually see we know how to find 1 divided by 1.05. We know how to do that. So we have 1 divided by 1.05. So there is our actual. In general, we're going to get to a place where we don't know what this value is. We don't. Obviously, if somebody said approximate 1 divided by 1.05, we would just plug it in, like we just did there in Desmos. But that's because whenever we do a new concept, we start with things that you could do another way. And do you see that the approximation is getting better? So the best linear approximation gets us accurate to 2 decimal places. The best quadratic approximation is getting us accuracy out to 3 decimals for sure. And then it will get better and better and better the further you go out.
That's good.
So the further you go out, the better the approximation will get. Make sense? So the idea, so it can get a little confusing what to plug in for x. So you want to do, when you look at this, we're starting with the function 1 divided by x. So x, if you look at that versus this x is getting replaced with 1.05. So over here, this x is the same x as that x. So if this x gets replaced with 1.05, then both of these x's get replaced with 1.05. So let's try that again with this one. So here, we've got a function. We're going to approximate it with a center at 4. We're going to approximate root of 3.9. And you should start to see that the center that we're picking is a number that you can evaluate the function at instantaneously. Right? You can plug the 4 in there, and 4 is a perfect square. Up here, we're picking a center of 1 because you can plug a 1 in there and simplify that easily and get 1. So we're picking a number that's close to the number you're approximating, that's easily whatever the function's doing to it, most easily functionable. You can plug it into the function and most easily do it. So 4 is the best perfect square that's close to that. So let's do the process again. And this is a process. We're going to rewrite y in a way that you can easily differentiate it. So I'll write it as x to the half. We're going out to 2 derivatives. So 1/2 x to the minus 1/2. If you want to get rid of that negative exponent, you can rewrite it like that if that's going to be easier for you to simplify it. Once you plug in your number, this one, of course, is square root of x. Y double prime, we're going to get negative 1/4 x to the negative 3/2, which we could write as negative 1/4 x to the 3/2. The next step is to evaluate the function and its derivatives at the center. So we're going to do y of 4, that's 2. We're going to do y prime of 4, that's 1/4. We're going to do y double prime of 4. So now we plug in a 4 down there. Square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32, so we have negative 1/32. So those are our 3 constants. So I'm going to write out p sub 2 this time, and then we'll just identify p sub 1 as part of p sub 2. So p sub 2, we start with the constant. Start with that constant. Now we add this constant, but we have to multiply by x minus what? X minus whatever the center is. So this is x minus a. So both of those are x minus a. If the center is 4, we replace that with x minus 4. So that part is p sub 1. So that's p sub 1. And so we can indicate that, we could just do this and say, okay, this part's p sub 1. Instead of rewriting it again and again, that's p sub 1 of x. Now to finish off p sub 2, we go to the next constant. And I'll write it as a numerator like that because we have to divide it by 2. And then we're going to have x minus 4 raised to what power? 2. It's quadratic approximation. So we'll get into the habit of this. You'll get really good at this because you're going to do it so many times and the pattern starts to be very obvious how you get to these coefficients. So the only simplification that we might do here, we want to leave all these x minus 4s, but we could write this as 1/64. That's the only simplification we're going to do. We're not going to square this out. We're not going to distribute that quarter. So that is p sub 2. And p sub 2 includes p sub 1. So the first part's p sub 1. All right. So now we want to approximate the square root of 3.9. So the square root of 3.9 is approximately equal to, so let's look at this. What is playing the role of x? We replaced x with what? 3.9. So we're going to come in here and going to go 2 plus 1/4 3.9 minus 4. This is going to be our best linear approximation. So our best linear approximation is going to be 2 plus 1/4 multiplied. When we do this subtraction, we get minus 0.1, minus 1/10. And it's probably going to be easiest if maybe we can do it in a couple of ways. If we write this 1/4 in front as 0.25, that might be a pretty easy way to multiply those two together. So if we multiply by 0.1, we move the decimal one more to the left. And so it looks like if I multiply correctly, and it's going to be negative, we're going to get 2 minus, so when we multiply that, 0.025. So this will be 1.975.
Yeah.
So that is going to be our best linear approximation. And then our best quadratic approximation. So all this stuff in front, this part right here, we can write as 1.975. And the only thing that we have left to do then is the quadratic term. So we have minus 1/64 multiplied by, once again, we're plugging in 3.9 right there. 3.9 minus 4 is minus 0.1. So minus 0.1 quantity squared. Now that is getting to the point where I cannot do all that in my head.
To approximate 164.
Yeah, what is 164? 1/64th as a decimal? That actually probably shouldn't be too hard. But my brain is fried. We're going Desmos. So we have, let's try to shrink U to a manageable size. Okay, so we're just going to plug all this in right here. 1.975 minus 1/64th multiplied by negative 0.1 squared. So that is what we get there. So let's just copy that over. That's easy enough. We've got that as our approximation. And now again, we are dealing with things that we can do anyway. We don't really need to do it with this linear approximation because we can just do 3.9 square root. But we are going to learn, whoops. I don't like that 5 up there with that little thing up there. Okay. So there we go. So that's the approximations. And the calculator is doing exactly what we're doing. But it's using an approximation, but it's going out further. It's using the same type of approximation, exactly what we're doing. It's just that the remainder has got to be smaller. Okay, so 1.975, that got us to 2 decimal places, accurate to 2. Almost accurate to 3 if you rounded that up. And then this one is going to be a little better. Let's see, 1.97484. So that gets us out to 6 decimal places? 5 decimal places. So we only did a quadratic approximation and we got accuracy to 5 decimal places. You don't have to go that far out typically if you pick the right center. If you can pick a center that is not close to this, so let's suppose we picked 1. You would just have to go out further in your polynomial approximation to get the same accuracy. But if you pick a center that's really close by, then your accuracy is going to come quicker. So that's kind of how it will work. All right, so that brings us to the generalization. can't remember if I logged out of Desmos or not. I created this cool little app that is, it's cool if I can log in. Is it gonna remind? I'm not logging in. I'll show this to you on Tuesday. Cool little app. Okay, so we're going to generalize. And notice that there's a little skosh of a change. When we look at this, see that denominator? We had a 2. And our initial suspicion was that the denominator was going to match that number of primes in the numerator. And it is, except there's one extra thing. If we were to do the cubic term, we would have gone through the math that we went through earlier to figure out C sub 2. To find C sub 3, we would end up with F triple prime over 6, not F triple prime over 3. And then if we do the next one, we'll see that the pattern in the denominator is not that it just matches exactly, it's that it's a factorial. So under the 3, F triple prime will be 3 factorial will be a 6. Under F with 4 primes, it's going to be 4 factorial. So that's going to be the pattern, is that we have an n factorial. And so that's it. So this is called a Taylor polynomial. So it's not a power series yet. Taylor polynomial is going to end here, and if we wanted it to be a power series, we would do this, plus dot, dot, dot. That makes it infinite. That makes it never ending. The Taylor polynomials end, right? So they are of a specific degree. So the tangent line is a first order Taylor polynomial. The best quadratic approximation is a second order Taylor polynomial. The best cubic approximation is a third order Taylor polynomial, etc. So the nth order Taylor polynomial is the best nth approximation to the function. If we write it in summation notation, that's what it looks like. The important part that we have just been playing with is finding these coefficients. So here is how we find the coefficients. We just take the derivative, evaluate it at the center, and divide it by whatever the prime is, the number of primes, factorial. All right. So let's look at an expanded picture here. So Taylor polynomial is just a generalization of a tangent line. And if we look at this, here is our best linear approximation. P sub 2 is our best quadratic approximation. And then P sub 3 is our best cubic approximation. And you can see that the alignment gets better and better. As you move further and further away from the center, you have a better and better match. They become indistinguishable for a longer period of time. You can imagine if you went out to P sub 100, P sub 100 is going to be indistinguishable from the original function for a long period of time, for a big interval. So that's the idea, is that the approximations start to match the function better and better and better. All right, so. All right, you all try this one. I want you to do P sub 1 and P sub 2, and then we'll do together P sub 3, 4, and 5. So see if you can do P sub 1 and P sub 2 for that e to the negative x. And they chose a center of 0. Center of 0. All right, so. And if you're feeling frisky, you can keep going and see if you can get all the way to P sub 5. P sub 5. Nice. Fill this up. How are your P's coming? Plausible. Plausible. Let's begin the fun with our function y equals e to the negative x. And so hopefully you're starting, a lot of this really is bookkeeping. And you want to write things in a way that you can keep track of a whole bunch of information neatly. So this one said we wanted to go out to p sub 5. So we will need to go down to the 5th derivative. So if you sort of use a table method and you think about columns of the table, first column is going to be the function and its derivative. Next column, we evaluate at the center. So y of 0, 1, y prime of 0, negative 1, y double prime of 0, 1. So if you got out to your p sub 2, you would have just that part. But really, the pattern is just continuing all the way down. So it's not too hard, actually, to go all the way out to p sub 5. So does everybody follow that up to that point? So we start with the function, take a bunch of derivatives, evaluate at whatever the center is. So it's easy to forget that part. You want to make sure you evaluate this at the center. You want to get rid of the x's in these these derivatives build the coefficients, and there's no x in the coefficient. Right? The x is coming from the form of the polynomial. So now if we form p sub 5, p sub 5, we start with this coefficient, 1. And then it's going to be minus 1 times x minus what?
0.
0. And so you don't have to write it as x minus 0. You can just write it as x. It's totally your choice. If it helps you to write it as x minus 0 so you see that center, do it. If you don't have to, then you don't need to. It's up to you. So right there, this is p sub 1. So p sub 1 of x is 1 minus x. So that's the tangent line. That's the best linear approximation. Now we keep on going. Now we add plus 1 multiplied by x minus 0 squared, but we have to divide by 2 factorial. 2 factorial and 2 are the same. So now you have p sub 2. So all of that is p sub 2. How is that, making it up to p sub 2? Once you see the pattern, it really isn't too crazy. And then we keep on going. To get to the third order term, we have a minus 1. Minus 1 multiplied by x raised to the third power. And we're going to divide by 3 factorial, which you can just leave it as 3 factorial. We want to identify the pattern. It's more obvious what the pattern is. So that takes us to p sub 3. P sub 4, we go to the 4th derivative. Bless you. We get plus 1 multiplied by x to the 4th divided by 4 factorial. So that's p sub 4. And then p sub 5, finish it off. Our last derivative at a value of negative 1. So it's negative 1 times x to the 5th. And we're going to divide by 5 factorial. That is p sub 5. So any function that has derivatives, you can build this associated Taylor polynomial. And eventually we will turn our Taylor polynomials into Taylor series. And those Taylor series will be an example of a power series. So we are starting with a function, taking derivatives to build a Taylor series, beginning with a Taylor polynomial. It becomes a Taylor series if it's infinitely differentiable, and we just put a plus dot dot dot. So if it doesn't end, then it's a series. If it ends, it's a polynomial. So Taylor polynomial versus Taylor series. Now there's one nuance here that is not completely obvious. When you create this Taylor polynomial or Taylor, let's suppose you extend it to a Taylor series, it's not obvious that the value of the function that you start with is equal to the value of the infinite series. So the infinite series is a function of x. The function you start with is a function of x. It's not obvious that they're identically equal. Like we manually constructed this with this derivative process. We've seen visually that we're building better and better approximations. But to say what we see on this very first slide here, that e to the x equals this, it's not totally obvious that that's true. It is true that you can build this Taylor series by doing the derivatives, exactly what we just did, and plug in 0. Notice that this is true on the whole real line for both of these. So no matter what x you plug in, if you want an approximation for e squared, you just turn all the x's into 2. If you want an approximation for e to the 5, just turn all the x's into 5. If you want an approximation for 1 over e, replace all the x's with -1. And it's true that those will be equal, but again, it's not obvious that the function you start with equals this never-ending polynomial, the Taylor series. We'll talk about why they're equal as we continue on. And it is true that if you have two power series that represent the same function, they have to be the same. There is going to be one and only one Taylor series or power series that represents a function. So the process that we're going through, we're building the Taylor series for this function. It will be equal to that function. And if somebody does something else, there's other ways to generate power series. You can find power series by integrating or differentiating other series. They will have to be the same. Let me point out something that is, let's see. Let's go to this slide here. So I want to just talk about, actually I want to go to the next slide. Let's just talk about some series in general, just to give you a little more context. So I broke the series into, there's 12 main series we're going to look at. I broke them into 6 and 6. So let's look at 7 through 12 here. So if you look at this first series, the exponential function, that's its Taylor series, that's its power series representation. You can say all sorts of things. Do you see a connection? Like we've talked a little bit about e to the x, and we saw that when we defined the hyperbolics could be turned into exponentials. Like the hyperbolic cosine was e to the x plus e to the negative x over 2. It was the average of exponential growth and decay. We've never seen a connection between e to the x in sine and e to the x in cosine. Do you see a connection there? Isn't sine all the odd powers of e to the x with a switch? Right? Sine is just these odd powers of e to the x with a switch thrown in. So there is a connection between sine and e to the x, and we will come to see it later. And similarly, cosine, isn't cosine just all the even powers? And we can remember that pretty easily because cosine is an even function, symmetric about the y-axis. Sine is an odd function. It's symmetric about the origin. So sine takes the odd powers, cosine takes the even powers, and then we throw in a switch. We alternate the signs. So you maybe have heard of Euler's formula, most famous formula in math. I mentioned it once before. Let's see. That's the most famous formula in math. It has the 5 most important constants in math all in one simple equation. You can verify that that's true by plugging things into a power series here, and you can get to that point. So that e to the pi I, you could come up in here and replace all the x's with pi I. We'll talk about how you could use these power series to get to it. There is a way to rewrite this one with sines and cosines. We can talk about that later. But, so, e to the x, if you have that memorized, it's very easy to get to sine and cosine. Sine of the odd powers, cosine of the even powers, and you put alternating signs in there. Notice the hyperbolics. So notice sinh and sine. Sinh is exactly the odd powers of e to the x. Exactly the odd powers. No switch. Cosh is exactly the even powers of e to the x. No switch. So you can get, if you have e to the x dialed, you can get to sine, cosine, sinh, and cosh instantaneously. Just a couple little modifications. Another power series down here we'll talk about later. We talk about the binomial series. That's the binomial series there. It is really just the geometric series, except that you have these funky coefficients, which we've talked about before, those coefficients. So that is the second group of power series. We might as well just spend a minute talking about the first 6. So the second 6, the generating function is e to the x. It creates all those ones except for that binomial series. This slide, everything is based on the geometric series. We already know the geometric series. The big difference when you write the geometric series as a power series is that you switch things around. We started with this side, right? When we're doing geometric series, we say, oh, if you have 1 plus a squared plus a cubed, etc., or whatever letters we were using, I can't even remember right now. We ended up with this. Now we're changing our perspective. We're saying, hey, this is a function, and we want to write it as a never-ending polynomial. And so we just changed our perspective. When we had a geometric series, we had the a and the r, and we figured out what it added up to, and we had the a over 1 minus r. Right? We had a over 1 minus r. We're just changing our perspective, and we're thinking of, okay, well, let's make a 1, and let's make r x, and just go that way. Now we're thinking of this actually as a power series for this function. We're now writing this function as an infinite series of powers of x. So we're going to change our perspective. If you integrate both sides, we will learn that you can integrate both sides of a power series. We can integrate this side and get that. You can just integrate term by term. Power series are really nice because they're polynomials. You integrate and differentiate the same way you do a polynomial, which is easy, power rule. So if you integrate both sides, you get that. And we now have a power series for this negative natural log of 1 minus x right there. Notice that these intervals are a little different. The ones that we had on the prior slide, they converged for every x, negative infinity to infinity. These ones have a limited, we're going to call this the interval of convergence. It's essentially the domain. These ones only converge if x is between negative 1 and 1, which we know that because we've already done geometric series. Right? R had to be negative 1 to 1 in order for convergence to happen. So, but we do notice there's a little modification here. When you integrate, we actually are going to include that endpoint. We'll talk about why later. This is the alternating geometric series. If you replace this x with negative x all the way through, you get a different series. You get that one. And then you can integrate that, and you can do some other things. We'll talk about these details later, but just to give you a sense of where we're going. These are the 12 series we're going to look at in here. It's not a bad idea to start looking at them and trying to establish some patterns as we go forward. All right, let's stop there. Enough math for today. For me. Maybe not for you. Oh! The pain! Cutting! Cutting! My femoral artery feels punctured. All right, have a good weekend because today's Thursday, right? Shockingly.
All that stuff, like what?
See you week 12.
His idea was to just tell you this in 2 hours and then send you on your way to the real world. Just go eat McDonald's now.
Yeah, good.